All right, very good. So let's start. Just like a hello, I'm here in Boca Raton, Florida. So I don't know where you're sitting. If it's like a cold in your place, I'm sorry. It is a nice day in Florida. A little bit about me. I'm Brazilian, I'm American, I'm Italian, but I was born in Brazil and raised in Brazil. And I work at IBM. I've been working at IBM my whole life. I actually started as an intern when I was going in college, and then I got hired and stayed because there was like so many different things that I did in my career that is just like looks like I'm working different companies and also like different countries, right? So that's why I've been in IBM for a long time. My title is Distinguished Engineer, so it's just an executive technical title and role in IBM. And what I call my cool factor is Master Inventor. I have that in my business card. And although like, the Distinguished Engineer is a very difficult process to go, the Master Inventor too, I think the Master Inventor always get the attention in my business card. People are like, wow, that's cool. So that's my cool factor. And my degree is in computer science. So I took my degree in University of São Paulo in Brazil. And I work basically with software development. When I'm not working, I like to travel. Not right now, I've been grounded as everybody. I like to cook. And I was playing Pokemon Go for quite some time. I think I got a break now, but was a little bit of playing with my employees and then with my niece and my nephew. So that's what I like to do. How did I start, like how I decided to go to computer science? When I was like growing up, I thought that actually I like things like architecture, design in the sense of like decoration, even fashion. So I thought I was going like more towards like this kind of like creation and ability to do these things. Although I was good like in the science, mathematics, but that's the part that was attracting me. And then in high school, I took my first programming class and I really fall in love with that. I love the idea of like having a problem and being able to go there and solve that problem. And also my mom, she was one of the first programmers in Brazil. And this was like in the 60s, like early 60s. So she always enjoyed the time that she was learning how to program and doing all the programming. She was working in a big company there in Brazil, and they have like, can you imagine those huge computers with like no memory at all and doing like all payroll and those kind of like initial business applications, right? So she was so excited all the time that she worked on this. And when I said that I really enjoy my computer class, right, and I wouldn't like to go and do my major on that, she was thrilled. My father is more in the creativity, advertising, and also an artist. And you can see like there is some of the paintings here in behind. So all this like creativity plus the how to apply this creativity to solve problems and innovations, I think that got to me in, with both my parents here. So what I'm going to do, I will start talking about this genomics, and the way that I frame the presentation is to understand the business problem before, because that's the way, when you go and to work in an industry or some even academia, you have like a problem to solve. So you need to understand the problem to solve, and then you can come up with the solution, the technology, and what's the right way to do. So that's what I thought about doing this. And because the problem that I'm going to show to you is in this genomics space, I said, let's level set some basic concepts of genetics, genomics, because for me, I got that in high school. So when I started working with genomics was a long time. Maybe for you it's not that long time and you know all this, but that's, and also we're going to talk about cancer. So if you're thinking about the body, you have a lot of cells, and in the cells you have the chromosome. You have the DNA, and then in the DNA you have all the genes, and the genes are the things that a lot of the genes and is actually common between all of us, but there are like some that define some characteristics like the color of our eyes or like the preference that we have. So there is a lot of different things that comes from our genes, and we say it's in our DNA, right? And in these genes, there is a lot of proteins and variations. And as we're like, those cells are reproducing all the time, our system, actually thinking about system engineer, our body is very good in quality assurance because you do all these copies and reproductions, and there is mutations that happens all the time. And our body is very good in discarding those mutations, let's say, and do like a quality assurance and keep us healthy. But sometimes those mutations will occur and the body will not be able to catch up, and that's what causes cancer, right? So genetic alterations will end up causing the tumors. Okay, now the next chart is what is the advancements on this area of genomics in the past 30 years? And 30 years is a long time. I know you're not born, but thinking about that, like in the context of healthcare, medicine, it's still like small time frame. In the 70s, so when we talk about genomics, there is a concept of precision medicine or precision oncology. And what that means is that instead of getting the kind of therapy like chemotherapy that try to stop every cell that's growing in your body, that's why you lose hair, like hair is trying to grow, you go there in a chemotherapy and you kill, right, like anything that's growing because you're trying to stop the tumor to grow. The concept of target therapies and precision oncology, precision medicine is to find that mutation that's causing cancer and then attack just that mutation. So that's the real idea behind precision medicine and target therapies, okay? The first one that was considered to be in this space was in the 70s. And then you can see here, there was some time, and during the 90s until 2003, this was the first time that the human genome was sequenced. That means the first time that they got the DNA, our DNA, and they were able to go to this process of sequence and mapping the whole genome of a person. And that cost $100 million to do the first one, and took like 13 years, which they thought was pretty good because they thought initially that will take even longer. But so they say it took only 13 years to map the genome and to understand the genome, $100 million, right? Then you fast forward a little bit, and then there is like some companies, this 2010 is a company that started doing this analysis of DNA for patients with cancer. So the company here is Foundation Medicine that did. Fast forward, you start like approvals. FDA is the regulation right here that approves any kind of like drugs. So they start like approving drugs based on those mutations, and reimbursement. So all this very relevant to the field. And if you're following the field, you may see like some of the Nobel Prizes that came like recently. One on the immunotherapy, that's a type of like those therapies. The other one is CRISP. CRISP is the ability of editing gene, okay? And now look at where we are. There is over 75,000 genetic tests available, and it's not only for oncology. There is, you can do your 23andMe and look at your heritage, right? You can do in vitro tests to see if the babies has any problems, like even like before. There are all kind of tests, and the average cost to do the whole genome is $1,000 now. So from 100 million to 1,000, huge difference. So what this means is that, you know, now it's possible to use all this in clinical, because with 100 million, who has that money, right? But now all of us is kind of affordable, especially if the insurance is paying. And just a little bit more data before we go like to the solution, but the data here is that we start looking at the impact. So is that really working? Because that's what matters, right? You can come up with all these ideas, but is that working? And there are some proof points showing that there are declines, and a lot of those declines are because of those target therapies. So you can see like melanoma, for instance, that a skin cancer, right? 7% decline in the death since like the first therapies of this category was approved. This is huge in cancer, it's huge. But even if you save only a few lives is huge, right? But 7% decline is great. Considering that you have probably 1.7 million new cases of cancer a year in the United States. If you think about the world, it's probably 14 million new cases a year. So a lot of people living with cancer, and being able like to help, it's huge, right? Now, what's the challenge? Well, many challenges. We're talking about cancer, but look at the information. So when you look at the information to be able to actually analyze those mutations, there is 16,000 new publications every month about cancer, right? And this is increasing. Like a few years ago it was 10,000, now it's 16,000. Same as COVID. You look at a COVID, there was no publications, and suddenly there is a lot of information on COVID, right? Number of drugs approved by FDA, over 300, I would say, since I did this chart. So a lot of this. In development, 5 years ago, there was 600 drugs in development. Now there is 1,200 or more drugs in development, accelerating. Look at the number of genes. Our body has 22,000 genes, 700 of them can be related to cancer. And if you look at all the possible alterations that you have in those genes, is over 10 million. So you need to know those 10 million alterations, which ones are benign, which ones are causing cancer, right? So that's the challenge for AI, let's say, is how you get that data and make sense out of this data. And just to put in the context of how this works is that when the oncologist that's here order a test to a lab, and they can order a test to a lab like Quest Diagnostics or LabCorp or all those more specialized labs like Foundation Medicine, Natera, right? The lab is going like to get the tumor, do the biopsy, etc. Actually, there is innovations in this space, and some companies like Natera, they are using blood now to do the test, so they can detect some types of cancer using you know, a drop of blood. That's huge also. Anyways, when you get to the interpretation that we're talking about, like, okay, now I need to make sense of all these mutations in somebody's tumor, that's when you apply the AI. And that's the, you know, not a lot of companies are doing that, but that's how we have like some of the research in the space, like, and the innovations in the space. And then you go back to the normal procedure, right? Now, when I talk about the 16,000 publications a month, that's how a publication looks like. So it's even hard for a human person like to read this, even if you are, you know, an expert in this space. Looks like those researchers that write those publications, they are trained to write in a language that's very hard to understand, right? It would be much easier if this was a few tables with like all the details there, but no, there is like a way like to write those long, and this is pages and pages of publications. And you need like to extract from this publication what's the bottom line, what's this publication is talking about. It's talking about EGFR is a gene, non-small cell lung cancer, it's a type of cancer. It's talking about another gene here. So what's really the bottom line of this paper, right? So that's when come the technology to help, to rescue. Okay, so the work that we did, and we did a publication on that, so you can actually go and, you know, read. If you want to read more details on the paper, you can check that. So what I'm sharing is work that we have actually make available for the public. But thinking about that, this is the publications, and it's showing 100,000 because 16,000 is related to cancer. 100,000 per month. It's all the articles that are published in this big library called PubMed, right? And you need like to look at those and then figure out which ones are related to cancer. So that's why we said 100,000 articles per month. The first thing that we decided to do was to use those machine learning classifiers and put that in buckets. And the buckets here that I have like in the labels here is like functional studies, clinical studies, predisposition, resistance. Why? Because in the beginning, we tried to apply natural language process here without categorizing, and it didn't work well, right? It was very, very difficult. Now, if we put in buckets, then the number of articles not only is filtering out a lot of things that are not related to cancer, not relevant to what you're trying to get, but also you put in these buckets that depending on the type of information that you're looking for, you're going to look at this bucket. So that's why if you're looking at like if a mutation is driving cancer, you look at the functional studies. If you want to know if a drug is working for a particular mutation, you look at in clinical studies. So that's why it's important to put in buckets, because then you can go and apply the natural language processing. And natural language processing, in this case, thinking about that you define entities and relationships. So you can say a mutation in the gene, a mutation name, V600E in the gene BRAF is causing cancer, right? Or you can say drug A targeting this mutation cause a resistance and it's not working. So that's what this natural language processing is doing. Here, there is a lot of post-processing information. In this particular case, what we are trying to do with this article was information that we already had in the database. So we have a knowledge graph with all this kind of information, and we're trying to see, is there new publications available there that I can go there and update, because maybe there is new findings. So thinking about the COVID situation that we're all familiar right now. So you get the vaccines, right? And there is the studies and the studies going there. So there was initial studies done, clinical studies that published results saying Pfizer will have this kind of efficacy, right? Like in the first dose, in the second dose, and then Moderna, and then J&J, and you have all this. So they got enough information, right? Clinical information to be able to approve and start using. But now they're doing more studies. And so they went to Israel, where they applied the vaccine to the whole population, 9 million people there. And they say, well, you know, can we do more extensive studies on the percentage of immunity that's causing the first dose versus the second dose, etc., and publish new data on this. So as they're publishing new data, and maybe sometimes you are not covering all the different races, so it might have some variation, like an African American will have like slightly different reaction than Caucasian, right? So as you're collecting more data, you're publishing. So that's why it's important to find, like, are there new information about the things that I knew, but either that emphasizes what I already know, or sometimes is yeah, it's against what I know, so it's disproving, and I need to take a decision here, right? The other example would be also like the AstraZeneca. People are saying that's caused some clots, and then they're like canceling, right? Like the stopping giving the vaccination, and the studies are showing that no, there is no correlation between that. You can continue. So that's why it's all important to find those additional, and then also. Other way to apply this is if you're trying to find novel things that you don't have in your knowledge yet. So something that was brand new, novel discover, and that was published, and you want to do, and you want to update. The last step here is that if you are talking about clinical, you need to have like a clinical validation. So that's why you always have the human. None of those technologies in the clinical side are replacing anybody. It's just like speeding up, right, and bringing all the information to them. So that's how it works, right? So now that same article, I'm showing you like a module that's we have. I can't remember if this one is the one that we annotated, because that's how you train the models, right? You go there and you annotate saying this is a gene, this is a disease, this is a mutation, and you show this like a few, sometimes 100 times until the system can process new information and start recognizing that. A few things are easy, like for instance, a drug, if you're saying like you need to take XX 3 times a day, that XX is probably a drug. Like after a while, you start understanding the context. The mutations, the genes were not that hard in the sense that, you know, at the end is 22,000 genes you can actually, you know, although sometimes they are referred in different ways, like the whole name of the gene or like the short name. But the mutations, oh my God, there is no, no good a pattern for that. So it really needs like a lot of training and then verification on that. So this one, I can't remember if was that something that we annotated or something that we process after, but it's basically to show like this is like the genes, the variants, the conditions, the disease in this case, and the drug, right? So that's how the system is doing. So after doing that, what I really, really want to find is what's the bottom line of this article. So I'm trying like to find, because maybe the same article may talk about a lot of different genes just as reference, but it's not like about that, the bottom line of that article. So the bottom line of this article was this mutation T79M in EGFR. It's a common mutation in lung cancer. It also causes resistance. So this is what happens is like persons start taking a medication, a drug, and they develop a resistance. So they need to change. So if you do the tumor didn't have that mutation before, the tumor evolved and developed that mutation that caused resistance. So what you need to do is in a new test, now you are showing this, so you need to change the treatment because the treatment is not helping the patient anymore, right? The original patient. So that's why it's important. And that's how the information gets integrated to that report that we're talking about, that the oncologists were ordering that report. So now when the oncologist is getting the report, it's saying this mutation that's showing up in this patient, it's called that it's resistant. So there's a lot of drugs are not showing, but there is a new drug here that's approved by FDA, and that one has sensitivity to this kind of mutation. So now you can change the treatment and start giving like this drug to the patient because it now will be effective to that patient. Okay, so actually, this is the presentation that I have. I know that can be very heavy to go, right? Like to all these terminologies and how the system works, but hopefully was, you know, good like to follow. if you want me to go back to any point of the presentation, I'll be glad to do.
Yeah, thank you for that. That was really interesting. It was really interesting to learn how do you actually implement those algorithms rather than just leaving it to the black box, you know?
Right, right, and good point, because transparency is also very important, right? And if you think about AI ethics and all this, right? In this particular, sometimes it is a black box. Sometimes there is like some magic happening, and in our case, there was magic. Like we're not like telling everybody how it's done, but once the responses were there, and here in the, it's coming. Actually, if you click here, it will go back and show exactly this document saying the reason that we said this is good is because this document is telling you there is a resistance here, but there is another drug. So there is the link and back to all the information, right? And the evidence. So it's not, there is the transparency that you're talking about, right? The transparency about like how, not how was done in the middle, but that result can be validated, that it came from a trustable source of information. That's important too.
That's really interesting. And I guess final question maybe is one that a lot of high schoolers have. And it's just what advice do you have for people who want to be or aspiring programmers and geneticists in terms of, what coding languages should you learn, what classes should you take, and just how you can put yourself out there, do research, all of that.
Right. I think it's a wonderful time to be, if you're interested in genomics, genetics, all that part, and the intersection with like technology, this is booming, right? Remember that those 30 years, now like the last, when I start working 7 years ago is being like that, I start work to now, it's like a huge difference, right? So there is a lot of opportunities. In terms of advice, I think that I think it took me too long to understand that the business side is also important. And so I think it's good always to understand, if you are working for a company, understand the strategy of the company, understand what your team is doing and how you're contributing to that company. So I think this is important career-wise, because if you're contributing to what the company wants to do, that's going like to help your career. If you're doing things that are completely different from the strategy, maybe will be hard, right? And maybe they will close that business at some point. Try to stay up to date, like reinvent yourself. My career, I didn't know much about biology, genomics, or oncology when I started. So I have like to reinvent myself a lot of times to stay relevant in the field. If you want like programming language, you're saying try to get to some of the foundational ones like Javas, Pythons, right? There is a lot of very cool technology that you can use in some ways. If you're interested in being like product development, you will need to get to a little bit more sustainable, easy way to maintain, because it was very common to people come programming some. I heard code in PL. What was the name of that one? Perl. I heard code in Perl. Oh my God, what a hard code like to understand and to maintain. I have like to learn that one to maintain. So it's good. All the time comes somebody and programming some other language, leave the company, and nobody knows how to, maintain that code. So that kind of balance of like learning different languages, etc. But then when you apply, know which one to apply for the right situation. And I think for most, like the problem solving, that's very important, to always try to understand the problem that you're trying to solve, then work in the solution, right?